So, ladies and gentlemen, my name is Pedro Vilaca. I am professor at Aalto University, and I would like to start by acknowledging the invitation to participate in this growing event from year to year in ecological and electrical aviation. So, Aalto University, I would like to start by introducing my institution. Aalto University is a young university with this name, but based on three old institutions, the technical, arts and business universities of Helsinki, with over 150 years old, and is located in a magnificent natural reserve of the Otaniemi Bay. And we have the honor of having this name of a world known architect and designer, Alvaro Aalto, who was a student, a professor, an entrepreneur, and as an architect, he also has all the sides of the mission on technology, science, arts and business of Aalto University, who is the most relevant university in Finland in this field. So I am the head of the Advanced Manufacturing and Materials Research Group, which is one of the 8 research groups at the Department of Mechanical Engineering of the School of Engineering of Aalto University. We are in this Advanced Manufacturing and Materials Research Group, we are 8 professors and about 50 staff members. Some highlights I would like to take the opportunity to introduce in advanced manufacturing related with additive manufacturing, and our Ed Lab is a key international partner in this field. We have the most important casting research facility in Finland. We are leaders in friction-based technologies, and the hybrid channeling, which is the innovation that I bring today to present you in terms of thermal management for aeronautic components, is one of those innovations coming from this line of research, and quality control and production management in circular economy are also on this scope. In advanced engineering materials, we are involved in the influence of hydrogen in materials and hydrogen economy, namely in the manufacturing of application of advanced manufacturing solutions in the production of PEM-based fuel cells. We also have distinctive research in multi-scale modeling of steels and in materials characterization, including microscopy, digital image correlation, and non-destructive testing technology. So, for today's agenda, we will start by evaluating and addressing the hybrid channeling. So what is channeling, what is hybrid channeling, and what are the benefits from these innovative manufacturing technology invented at Aalto University. So the need for thermal management in electric aeronautics will be overviewed, and we will close the presentation with 2 application examples, one for exercise for electrical motors and another one for battery cells. And we will then close with the wrap up on conclusions and summary. So, hybrid channeling aims at thermal management systems, producing or delivering solutions that are safe, compact, and lightweight, as demanded by the high power density propulsion systems, high energy density storage and power electronics, and many structural components. So what is channeling? Channeling is a manufacturing method that enables to produce subsurface channels in massive domains in a single operation. These channels closed channels, so subsurface channels, can have any path, and variable or constant shape and being produced at different depths. The innovation of hybrid channeling is a big jump in terms of the opening of opportunities for design and structural design and design for thermal management also in particular. So hybrid channeling is an innovation and an invention from Aalto University, where besides all the benefits from channeling, we produce a weld, and so we are able to combine different materials or different thicknesses, and so we have now a higher level of freedom for tailored optimal design for structural and thermal applications. So we produce these by using a non-consumable tool that has features that extract material from inside and a tip that produces the weld. All these done in one action, combined action. All this is done in a domain of viscoplastic third body domain, which lays between the liquid and the solid. And because schematic representation and films address this better, you can see then a representation here where the tool produces the internal subsurface channel while producing the weld between two different materials here, an aluminum alloy and a copper thin plate. On the right now you can see a film of this hybrid channeling being applied in manufacturing of conformal cooling paths, combining two different materials, different aluminum alloys in this situation, for a radio network system that operates right now with the 5G and what's going to come at very high power densities also. One of the prototypes that has been produced and is now running inside of electrical vehicles in partnership with a recent startup, Finnish startup, that produces modifications from combustion to electrical engines in classic cars, is being applied. And you can see there, we have a thin copper sheet that produces the management, and then the thick aluminum produces the management of the copper sheet. So the copper is heavy and expensive, but has high temperature stability, corrosion resistance, and thermal conductivity. So we reduce the cost and the weight by this lower cost and lightweight aluminum that does the thermal management. And this thermal management in particular takes advantage of quasi-null contact thermal resistance between the components. This is a major advantage compared to most of the solutions where you have different materials and a coil of copper or aluminum contacts the other bodies. Other important advantages of hybrid channeling are brought by the roughness of the surface, and the improvements of up to 50% are found when we apply air as cooling media. This means that we can use air in domains where only liquid before was possible to reach. This is due to the irregular and multidirectional rough fractal condition of the surfaces, also delivering high surface per volume and promoting an early onset of the turbulent flow at relatively flow rates even. So you can see some of these features in this optical 3D scan of the top and the ceiling surface and side surfaces of the internal subsurface channel in this slide. We have proved that it's possible to apply the process in complex spirals, sharp curves, and with really complex and tight low radius curvatures. So the design and the conditions are able to address complex design demands. Other important features, the internal pressure for burst and leaking has found to be over 350 bars, most of the times over 400 bars. This is higher than any specifications in heat transfer applications that I know. So this, along with very low leak-free test result, where most of the problems always comes from couplings compared to the leak-free condition of these channels. So there is a perceived need for thermal management in electrical aeronautics. This is important if you consider, as an example, a 60 kilowatt rotor power in a propulsion system. At 95% of efficiency, you have a dissipation of energy, mostly in heat, of about 3 kilowatts. This will, without proper safe and reliable thermal management, will lead to loss of integrity of polymer insulation, thermal fatigue, problems induced by different expansion factors of the different engineering materials that are made, these components are made of, and corrosion induced due to the higher level of energy in operation and complex chemical environment. This is well known, nothing new here. We know this from a much more mature application in automotive. So the thermal runaway, loss of control by mechanical, electrical, thermal abuse inducing short circuits are well known. The problem is that it cannot happen in flights. When it happens, really, unfortunately, but not unexpectedly, the development has some drawbacks in all the technological relevant evolutions. And we also know some recent crashes related with batteries for this situation, apparently, of the electric Magnus effusion in 2018, or more recently some components from the energy storage of these Aviation electrical plane also got fire. And so it is obvious that the safe operation of electrical aviation depends on a proper thermal management for high power propulsion systems, high energy density storage device, power electronics, and the structural components that demands de-icing as an example. So I will now introduce two exercises that are ongoing in terms of prototyping towards piloting. And the first one is an exercise of application to an electrical motor, where we provide a solution that is integrated in a stiff structural system. So the thermal management is not an add-on feature. This enables a compact and low-weight solution. In this slide, you may see the components. We have a stator cover that is made of thin copper jacket that is cooled by helicoidal ribs in aluminium with two channels, and then we have the hub cover and the end plate. But let's see this in a little bit more detail. You can see in this detail the two channels, hybrid channels, where the aluminium rib is welded to the copper jacket. The copper jacket promotes the internal environment, and the liquid for cooling circulates within the rib that is with non-relevant thermal resistance in contact with the copper, and so all the liquid runs outside of the system, and so any leakage also would not be catastrophic in contact with the electrical circuit inside of the electromagnetic electric motor. So the hub cover, we plan to provide some thin copper fins that are welded to the body, where we have to the cover, where we have two channels providing the thermal management of these fins, and they go inside with no contact with liquid again, providing the local all around surface thermal management. We have the same for the end plate, and then we can close the system again using thermal management with hybrid channeling. So one same process is able to produce the components that the engine is made of, providing at the same time the thermal management. More details in terms of perspective on the up cover with the copper fins and on the starter cover and the final system. So, in summary, we have these 8 subsurface channels, 3 in the up cover, 2 in the starter cover, and 3 in the end plate. All of them are compact in design, and they are safe in operation as they separate the liquid from the electromagnetic domain. Other designs can be expanded from these for more complex and higher power engines, namely with double starter core. For the battery cells, we have several solutions. It's quite mature field of technology, the storage of energy, and solutions exist, but none of them provides the reliability at the level and the operation capacity at the level that aeronautics demands with a lightweight solution. And for that, we now have prepared, and this is a new patent from Aalto University, okay, a direct assessment of each one of the cells, cylindrical cells, prismatic cells, pouch cells. We can have straight or waved channels that are ribs that are welded to the aluminium fin that involves all the battery, and we can encompass 1, 2, 3 more units with one fin or more fins coming from the same rib. The concept accesses all the surface with emphasis also for the anode and the cathode zones, and it takes air in an aluminium structure, so extremely light, in a very short path, so there is no saturation of the airflow, and it takes advantage of the self-convection plus the force that can be controlled by several electrothermal components like Peltier components. So these are some more details where the implementation in a battery cell model is here represented with the 3 parallel times 16 series of 48 cells. The advantages of this concept in terms of lightweight and safety are very relevant, as we are able to provide with air a domain of application that only a liquid typically can access. And we have in this slide a summary of the benefits addressing the efficiency and uniform thermal field, because each channel accesses a very small number of elements, and there is no saturation over a long path. It's light and simple, which is very important in terms of reliability. It's safer as it uses, so any air leakage is not hazard for the electrical circuits and the electronic control units, and is compact, as space is also important besides in aeronautic, beside the weight. So, in conclusion, I summarized some of the benefits. There are challenges, naturally, to any related with any innovation in manufacturing, but we can provide an optimized multi-material solution in self-stiffened structure. Thermal management is fully integrated in structure, and it's not an add-on feature. So we also have this benefit in terms of complexity reduction and weight. And this lightweight is already addressed by the optimization of the thickness and the materials. It's efficient, as we have been evaluated in experimental implementations and modeling. Cost efficient, it is, we hope it will be, and because we have the minimization of the material, and we are able to perform with one action a complex operation of opening channels, closing channels, and producing the welds between different elements. Reliable, robust, and sustainable, as it is the name of this conference, with the ecological approach. The process is a solid state process where no fumes, shielding gases, radiation are emitted, and the efficiency of the process is also quite high. So, with this, I conclude my presentation, and I hope I acknowledge your attention during this period, and I'm opening to any questions now, and because this will be recorded, my email is available for later questions from anyone registered in the conference. Thank you.
Thank you very much. There is a question I'd like you to elaborate a little bit more. Your technology is under development, and the sort of inventions, the creative part is already there, but then it needs to be manufactured. How competitive do you think that will be in the market? In cost, how cost effective and competitive it will be?
It has all the conditions to deliver a high competitive cost efficient solution. We minimize the amount of material and we also minimize the cost of that material by the combination of multi-materials. And in one operation, we produce a complex manufacturing process. So the conditions are created to deliver that. We are in a stage of prototyping and piloting. This is not cost efficient at all. We need partnerships, and we look forward to get those. Also, I take the opportunity to say that we have an entrepreneur action, and a new company has been set up and will be ready also to have the relation, a commercial relation, and not only this research relation that the university will provide in backup.
Thank you.
Okay.
Yeah, thank you. Another question. You saw there are some parts which were actually curved plates.
Yes.
So how easy or difficult is to use this technology for curved parts?
Yeah, we have done it. So all the manufacturing, because it's a complex action, combined action, demands some mastering, and this is the reason why this innovation has value, has an inherent value, because it's supported by key knowledge that exists in Finland at Aalto University and is being transferred. So it is possible. It will always be challenging depending on the radius that we need to access. But we also are able to provide designs for thermal and structural applications that are in line with the capacities of the manufacturing. Anyway, non-manufacturing solution is able to solve everything. So obviously that we need to encompass what exists best in the world.
Yeah. Thank you about that. Still some more. You're saying that air is, you would like to use air as a taking the heat away.
Yeah.
So do you think that it could be like outside air also, or must it be circulated air?
Yeah. we need support from aeronautic engineers to decide on that. We have the benefit is that we really, with the features, with internal surface features of the channel, we are really able to get a very high heat transfer capacity with air that was never able to perform before with the other manufacturing solutions. For aeronautic, this is absolutely key. The air source can be internal and doesn't need to be treated, so it can be air that is used in some bad environments and can be later used for this. And we can even take hot air and with relatively low amount of electricity, and electricity is not the problem in electrical aviation, it is the managing of the safety that is the key issue, and reducing the weight and produce compact solutions to be able to make it also reliable and feasible economically to explore the electrical aviation.
Thank you very much, and we have got a very interesting question. Can this technology used at low temperatures like liquid nitrogen or something similar?
It encompasses other features, because when we go to that range of temperatures, the impact toughness of the materials start to play a role, and we need to evaluate the structural performance depends. So the answer is it will depend on the scope of the application and the level of toughness that we will need from the materials. It is ready to do it, but we need to evaluate the viscosity of the fluid that will be used, and at that range of temperatures, and the toughness of the materials and the joints that are inherent to this manufacturing operation. So this is an engineering solution, and we need to provide the best of our knowledge to any of those. But just being able to address those things are magic moments already. So this means that we are in the right track somewhat.
Yeah, maybe I'll follow up on that. I think that you mentioned that, in order to produce reliable solutions for aviation, temperature control is critical for example, in batteries, in aircraft, for safety. So do you think that technology could be used to automatically control the temperature and possibly design emergency procedures to control the temperature or shut down and that sort of thing? So is that the automation easier with this technology that you have shared?
There is no limitation from this manufacturing technology. It enables to encompass from the manufacturing implementation to the operation, a control and a digitalization approach in all the stages. There are for urgent thermal management, peak moments, we need to address these, because this solution provides great conditions for transient domains, but there are limitations for air heat transfer, and so we need to have some ultimate safety conditions. So just for you to have an idea, so we are able to get about 700 watts nowadays with a relatively 200 by 300 plate of copper with a rib of aluminium, a small rib of aluminium. This comes almost to 1 horsepower of heat transfer with water. With liquid, we are able to get 100. So for urgent action, we always probably will need some storage of liquid source for ultimate safety. It again comes to the design and to the certification societies in this domain. But we cannot take the worst case scenario in permanent operation. That is not engineering done in a rational way.